Welcome to this video on drawing free body diagrams. In this video, our main goal is just to go through the process of drawing a free body diagram with some basic examples. The first thing we want to make sure we understand is that the point of a free body diagram is that it's a tool. It just helps us analyze what particular forces are acting on an object, the relative strength of each of those forces, and then also the direction that that particular force is pulling the object or pushing the object. And what we do with these is we use them to make calculations or predictions after we've done some sort of basic analysis, and we'll get to that in a couple later videos. So in order to go through the steps here of how to draw the free body diagram, I'm going to do this very simple example, and then we'll do a couple more just to solidify the process. Okay, the first thing is we have here in example 1 a box at rest on a table. Well, the first thing we need to do is identify the object. We have two options here. We have a box and we have a table. I'm going to focus on the box. That's going to be my main goal. So just make sure you know what the actual object is, because that can alter how the free body diagram looks. The next thing is we're going to do here is represent the object as a center of mass. It's just a fancy way of saying condense all the object down into a dot or a box. So in other words, we don't care about what the shape of the object is, we just care about the mass of the object. And so we're going to draw a dot here to represent the box. That's my object. Now I'm going to show arrows. Each arrow is going to represent a force that originates at the center of mass and points in the direction that the force would move the object. So the object might not be moving, but we're going to draw it in the direction it would be. Every single free body diagram that you draw for most objects near the surface of the earth, or even not near the surface of the earth, are going to have a force vector that points down towards the center of the earth, and that I'm going to label force of gravity, F sub g. So my label includes the type of force. So I've just drawn in the type of force. Now I'm going to list the agent and the recipient. Well, the recipient is always the object that you decided to draw the free body diagram for. So in this case, that's going to be force of gravity on the box, and the agent, or the thing doing the force or applying the force, is going to be the earth. Now truly what's happening is the earth and the box are pulling on each other, but we are going to do it in this format just so we have some sort of structure to our diagrams. So we drew a dot, we drew the arrow in which direction the box would get pulled. So the box is getting pulled down towards the center of the earth by the force of gravity that's acting on the box, being done by the earth. Okay. Next, what we need to do is decide on any other forces. Well, we know the table is pushing back up on the box, and that's what's keeping it at rest. So I'm going to draw an arrow here going up this direction, and if you remember from the catalog of forces, we're going to call this a normal force. It's a contact force between the box and the table. So again, this is acting on the box, and it's being exerted by the table. So if you look at this example here, the box is always the second word in the label because it's the object that is the recipient. It's the whole point of why we're drawing the free body diagram. Next, we're going to do tally marks to show relative magnitudes of the forces. What we mean by this is show if one force is stronger than another. Well, in this case, because it's at rest, and we'll get into this in more detail later, this object is balanced and it's not moving, so these two have the exact same strength of force. So I'm kind of showing it in that way. So that's, fairly straightforward. Just make sure that you actually go through the process, even with the easy ones, so that when you get to the harder ones, it's easier to do. Okay, let's go to example 2 here, and we'll take a look at adding just one extra element to the problem. In this case here, I have a box at rest on a table with a book on top of it. So now I've got three possible objects. We have the box, the book, or the table. Again, what I'm going to do is say that we're looking at the box. So let's go ahead and draw the force diagram for that, or a free body diagram. So I'm going to start by drawing a dot to represent the object. Again, I'm always going to have the force of gravity acting on the object, so I'm going to go ahead and put that on there. So the force of gravity is acting on the box, and that is being exerted by the earth or interacting with the earth. We know it's still on the table, so the table is going to have a normal force pushing up on it like this. So I'm going to write here force normal acting on the box by the table. Now I was thinking ahead a little bit, and you see I drew this longer than this one. So this is 2 units long. This one's 1, 2, 3 units long. And the reason I did that was I know it's at rest. So the upwards and the downward forces have to balance, meaning that there's a force pushing down by the book. And so what I'll do here is I'm going to use a different color and I'm going to draw that force in. Well, if this is 3 units up, then there have to be 3 units down. And right now there's only 2. So I'm going to go ahead and draw the one pointing down like this. And what I'm going to call that force, I have a couple options. I could either call it the force gravity on the book or on the box by the book, or I could call it the normal force. And it truly is actually a normal force in this case because it's pushing on, there's a contact force. So I'm going to say it's a normal force acting on the box by the book. So here I see that if I was going to do my tally marks, let me change colors here, I might put 1 tally mark there, 2 over here, and then 3 over here, just to show that this is how the whole situation balances out. So this is a situation where we had 1 extra force here. It's still balanced even though there's an odd number of forces. All right, let's jump to the next example. All right, this example is a table being pushed across a classroom floor at a constant velocity. So the object in this case is going to be the table. I'll go ahead and highlight that. And let's use blue to draw this one. All right, so here's my table. Again, I pretty much will always start with the force of gravity because I know that's what's always going to be present. So I'm going to say I have this force of gravity acting on the table by the earth. All right. And then I'm assuming the table is not sinking into the ground or, accelerating downwards. So I'm going to draw an upwards force that's going to be exactly the same length as this one. And this is going to be a normal force still acting on the table by the floor. You could put ground or whatever else you wanted. Notice that the key thing here is that the second word on the label is always the same for all the forces because we are drawing a force diagram or a free body diagram for the table, not for anything else. Okay, now it didn't say what direction this table is being pushed. I'm going to just say that the table is being pushed to the right, and that's how I make that decision on my own, unless otherwise stated. So let's say that it's being pushed to the right, so I'm going to draw an arrow pointing to the right, and I'm going to call this one an applied force. And I'm going to say this applied force is being exerted on the table, and I'm going to assume it's being pushed by a person. So force applied on the table by the person. Awesome. Okay, now it says that we're moving at a constant velocity. Constant velocity, and this is getting a little bit kind of a review of the other concepts that we talked about before. Constant velocity means that you have to have balanced forces. And if you have balanced forces, what that means is that they have to point in opposite directions and be the same magnitude or strength. So in other words, I have to have something pointing in this direction so that these two balance out. Well, that turns out to be friction in this case. I'm going to put force of friction. That's acting again on the table, and it's exerted by the surface or the floor. Okay. So now I've broken into something slightly different where I can have vertical and horizontal forces, and the vertical forces balance out and the horizontal forces balance out. So there we have that example. Now here in contrast, we have an example where it's a table being accelerated across a classroom floor. Accelerated here is a key word that is different than here where we had constant velocity. So accelerated is going to imply that we have unbalanced forces. Now they don't have to be unbalanced in both the vertical and the horizontal. It could be just one or the other. So unbalanced forces, I'm going to go through my process again. Start with a dot to represent the object, which in this case again is the table. The vertical is going to be exactly the same actually, so that's easy. So I'm going to go ahead and just quickly sketch those ones on. Force gravity on the table by the earth. We have a normal force on the table by the floor. I'm assuming again it's being pushed to the right, so I'm going to go ahead and draw my force applied here. Force applied on the table by the person, and then I'm going to say there is still friction, but I'm going to make my friction unbalanced. So I'll make it smaller, and I'll call that force of friction on the table, again by the surface of the floor, whatever you want to call it. Now I want to show that these are different amounts, so I might do 2 hash marks here and just 1 here, just to kind of show the difference. Now I'm going to assume the table is has a higher force than what the force applied is. So I'm going to change this to 3 here, but it doesn't really matter as long as you have relative differences between the forces. So here you can see we have an unbalanced situation. Here we have a balanced situation, whereas the vertical are balanced in both cases. In the next video, we're going to take a look at how do we take this information and then put it into the context of being able to make a prediction.